Okay. So here's a Zoom meeting for Physics 231C. We're right there. We're finishing September. And earlier this week, there was an exam. And now there's the corrections exam to do. The results on the exam are not out yet. We have to wait until the corrections exam is finished. So the results for the exam will probably come out this weekend. They were pretty good on the average. The average score was more than 9 out of 12, if I remember correctly. And that can be increased by doing the corrections exam and getting bonus points. Anyway, that's completes chapters 1 through 4. And now we go on to chapters 5 and 6. They'll be combined in the next 2 weeks. So well, 2 weeks since the 27th. So some people have already started doing the reading quiz for chapter 5. There's also a reading quiz for chapter 6. It's split into 2 parts. So it's sort of like a double assignment. It's longer than the other assignments, but you have more days to work on it. So just look carefully at Log Kappa to find out what the dates are. All right, so chapter 5 is on energy, or it's actually called work and energy. Energy is defined at the same time as the concept of work. Now, everyone knows that energy is important. After all, we pay for it, we buy it. It's not cheap. But what is it? I mean, when you buy gasoline, that'll provide energy for your car. The gasoline will burn inside the engine, and that'll drive the car. But gasoline is not energy. Gasoline is a distilled product made from petroleum. So what's energy? Gasoline has energy, but gasoline is not energy. You eat food every day to provide the energy for your life. Energy, I mean, food is a kind of fuel. It's like gasoline is fuel for your car. Food is fuel for your body. But again, food is not energy. It's just that food contains energy. So everybody knows that energy is important, but how many people really know what it is? Now, energy was invented in physics back in the 19th century. And you probably studied energy in grade school, middle school, high school. You probably learned some things about energy. But again, what is it? One way to define energy is the ability to do work. But then that raises the question, what is work? And when you say energy is the ability to do work, this is a kind of jargon. It's referring to the technical physics meaning of work. Work is force exerted through a distance. Well, we've studied forces back in chapter 4, so we all already know about force and distance. Now we're introducing the concept of work, which is multiplying force times distance, and energy, which is the ability to do work. But that's not a very good definition. I mean, it's, what's the energy in gasoline? Makes it possible for gasoline to do work. Probably the physics definition of energy is more mathematical and more subtle. In physics, throughout physics, and not only physics, but all the sciences, energy is a conserved quantity. It's a quantity defined by a consistent set of equations. In fact, energy is not just one thing. There are many different forms of energy. And in chapter 5, we'll learn about 2 forms of energy, kinetic energy and potential energy. So energy is many things. There are many different examples of energy. But for each example, there's an equation. So really, as far as physics is concerned, and that's where the concept of energy starts, it's a quantity defined by equations. Now, we'll be studying in this chapter energy in mechanical systems. Later in the semester, we come to thermodynamics. That'll be, I guess, in November. Energy is important in the theory of thermodynamics. Thermodynamics is the behavior of heat, temperature. Energy can be transferred from one part of a system to another part of a system. And there are really 2 ways in which energy can be transferred. One way is by work, and the other way is by heat. So the first law of thermodynamics, the most important starting point for thermodynamics, says that the change of energy for a system is equal to the heat added to the system minus the work done by the system. Well, we'll come back to that in November. If you have an isolated system, that is to say, it's not in contact with anything outside of itself, then the change of energy in any process must be 0. Because in order to have heat, you have to transfer energy from one material to another and change the temperature. Well, if there's only one isolated system, there's no place to transfer it to. So Q would be 0. And again, if it's an isolated system, it doesn't exert forces on anything. And so nothing exerts forces on the system you're talking about. Work is force by distance. Well, if there's no force, there's no work. So for an isolated system, the change in energy in some process must be 0. And that's called conservation of energy. Conservation means constant. As the system evolves, the energy does not change. Energy is a quantity. Well, the quantity remains the same. Now, it can change from one form to another within the system. But the total energy possessed by the system would be remaining the same. So if there's a transfer in one way, there has to be another way that transfers it in the opposite direction. There could be one positive transfer of energy balanced by one negative transfer of energy. So this is a great conservation law in physics and in all the sciences that says that energy is conserved unless the system you're talking about is transferring energy to another part of to something else. All right, so that's kind of the basic idea of energy, and now we need to look at the equations. So here are equations from chapter 5. You're going to need these equations for the homework, and we'll look at some example homework problems in a minute. You're going to need these equations for the second exam. So, write down the equations in your notebook. When you read chapter 5, take notes, about 1 page of notes front and back for each chapter, and make sure you have all these equations understood and remembered and written down. So section 1 is about work, and the work done by a constant force is the force times the displacement. Now remember, displacement can be positive or negative. Force has a direction, so that direction could be in the positive x direction or the negative x direction. So the force could be positive or negative. The displacement could be positive or negative. The product could be positive or negative. So there's such a thing as negative work. Seems a little weird. In everyday life, we think of work as something you do and you can't undo it. I mean, there's nothing in everyday life that you would call negative work. But in physics, work can be both positive and negative. Now that would be for one-dimensional motion. If you had two-dimensional motion, then the work would be, work is always associated with a force, some force. May not be the only force acting in the system, but some force acting in the system will be doing work. And in 2 dimensions, it would be Fx delta x plus Fy delta y. Force is a vector, so it has an x component, a y component, 2 directions. Displacement is also a vector. So this is sometimes called the dot product of the force vector with the displacement vector. But this is the way to think of it. It's Fx delta x plus Fy delta y. Now that's if the force is constant. But what if the force changes as the position of the object you're talking about is changing? Then, so F depends on X and Y. Well, then what value of X and Y would you put here? What value of X and Y would you put here? Well, if F is constant, it doesn't matter what values you put there because it's just a constant. But most of the problems we'll be concerned with are problems where F is not constant. So this would be a way to start, but we have to go further than that. We have to say, what's the work done by a variable force? And the answer is you take the motion of the object that the force is acting on, divide it up into many small pieces, delta x. Here, delta x means the change in x, the final value minus the initial value. Here, delta x with a lowercase delta means a very tiny change of x. And so Fx means the force at the position of that little change in x. So Fx delta x is the work done by a force which, for a small change, I can just think of it as having a constant value over that small change, times the distance. But now you have to sum over all those little portions. So it's the sum fx delta x, where delta x is very small. Let delta x be, I don't know, a millimeter. Over that 1 millimeter, the force won't change very much. So I can just call that the value of F in that little 1 millimeter space times the 1 millimeter. That gives me the work done for that little part of the motion. And I add them all up if the object moves by, say, a whole meter, with F changing as it moves around. Again, that would be in one dimension. In 2 dimensions, you would have the same thing, only you would take this dot product and sum over many small segments of the change. Now, you can visualize this graphically as the area under the graph of force versus position. So suppose you're moving in one dimension, you move from here to here. So that full change is delta x. But let's say the force is different at different points along the trajectory. So you divide this up into many little pieces. And you calculate the sum, fx delta x. Well, now if you think of a force, a graph of the force, this would be the force in the x direction, as a function of position, then, for each little displacement here, the force has a different value. Let's say the force is increasing. So you have the force times the displacement. That gives me a little rectangle. I don't know if I'm going to be able to draw this. For each displacement, I get a little rectangle, because the width times the height is the area of that rectangle. So I get all these little rectangles, and I add them all up. Well, the result is the area. So work and visualized in graphical form, work is the area under the graph of force as a function of position, where the position is changing from one end to the other. One example of a force, which actually we won't come to until the next chapter, but an example of a force is Hooke's law. That's when you have a force that is a linear function of x. I've drawn this as a linear function of x, but this is increasing in x. A spring exerts a force in the other direction. If I stretch a spring, the spring pulls back. So the force is back. The force is negative. So the force is negative, some constant times x. The constant would be the slope of this graph. The work done by the spring is the area under the curve. Well, there's this minus k. So minus k over 2. The area under the curve will be x2 minus x1 squared. Sorry, x2 squared minus x1 squared. It's the average value minus the total change in x. That's the work done by the spring on the object that is attached to. But on the other hand, by Newton's third law, the spring exerts a force on also the other end of the spring. So there's work done, the object that it's attached to exerts a force back on the spring. That's Newton's third law. For every action, there's an equal but opposite reaction. So that means the force done on the spring would be the same, but opposite. So negative becomes positive, 1/2 k x2 squared minus x1 squared. All right, we'll see examples of spring forces a lot more in chapter 7. All right, so that's a variable force. A force which is different at different points in space. Like the force exerted by a spring, as you stretch the spring, the force gets stronger. The more you stretch it, the stronger the force is. And it's in the opposite direction from the stretch. If you stretch it to the right, it'll pull back to the left. That's section 2. Then there's section 3, which introduces a kind of energy. So far, we've only talked about work. Now we come to energy. And the first kind of energy is kinetic energy. And that has a very simple equation. The kinetic energy of an object moving with a speed v is 1/2 mv squared. M is the mass of the object. So kinetic energy is a combination of both mass and speed. But it's not mass times speed. It's mass times the square of the speed divided by 2. That's the definition of kinetic energy. And the reason it's defined that way is because of the work kinetic energy theorem. That says the change in kinetic energy, if an object is moving, is equal to the net work done on the object. As an object is moving around in space, it'll have one or more forces acting on it. You add up all those forces as vectors, you get the net force. You remember from chapter 4 how important that was. The net force produces acceleration. Well, it also produces a change in kinetic energy. The change in kinetic energy is just the work done by the net force. So work is a kind of energy, but work isn't really an energy. Work is a transfer of energy. So it produces a change in some sort of energy. In particular, the net work produces a change in kinetic energy for a moving object. And this equation will be used in some of the problems. Then the next section is on potential energy. So we've studied one kind of energy is kinetic energy. We sometimes think of that as the energy of motion. Kinetic energy does not depend on the position of the object as it's moving around in space. It only depends on how fast it's moving. It doesn't even depend on which direction it's moving. It's just 1/2 m times the speed squared. See, this is not a vector. This is the magnitude of the velocity vector. But the magnitude of a vector is a scalar. So kinetic energy is a scalar quantity. It's not a vector quantity. Although it depends on a vector. It depends on the vector v, which I write as velocity v with an arrow over it. But it doesn't actually depend on the direction part of the vector. It really only depends on the magnitude. The speed. Now, potential energy is sort of the opposite. Kinetic energy depends on speed. Potential energy depends on position. So kinetic energy depends on speed, but not position. Potential energy depends on position, but not speed. Potential energy is not defined for every kind of force. Potential energy is defined for certain kinds of forces, which are called conservative forces. And the definition is the change of the potential energy when the object you're talking about undergoes a displacement is minus W times the work, minus W, that is to say, the negative of the force times delta X, or if it's a variable force, the sum of F dot delta X over all parts of the trajectory. So delta K is the net work. Delta U is defined as the negative of the work done by any force that's acting on the system. This is not necessarily the net force. If this object has three forces acting on it, then there'll be three kinds of potential energy. There'll be delta U1 is minus F1 dot delta X. Delta U2 will be minus F2 dot delta X. Delta U3 will be minus F3 dot delta X. And we have a definition of potential energy for every force. Now, since this only defines the change of potential energy, we need to have a reference point, which we sometimes call X reference, which is the point where we say the potential energy is zero. That's kind of up to us. We find a convenient position, since potential energy depends on position, we find a convenient position where we can say the potential energy is zero. We could use a different position. We just find a convenient one. And then this tells us how the potential energy changes as you move away from that position. Here's one example of potential energy, the potential energy of a spring. If you have a spring with spring constant K, so the force is minus Kx, the energy is 1/2 Kx squared, where X is the amount that the spring is stretched. Or you could have a compression spring. So X would be the amount that the spring is compressed. X is the distance. It's really the displacement from the equilibrium point, where the equilibrium point is when the spring is neither stretched nor compressed. At that point, there's no force. It's only when you stretch the spring, there's a force back towards the equilibrium. When you compress the spring, there's a force back towards the equilibrium. The potential energy for a spring which is either compressed or stretched is 1/2 Kx squared, where again, X is the magnitude of the displacement. Now, usually a spring is one-dimensional. So we usually only have one coordinate for the dimensions of the spring, but we could have the spring laying out in the XY plane, for example. Here's another example of a force and its corresponding potential energy. Gravity is a conservative force. The conservative forces are the ones that have a defined potential energy. Well, gravity is a conservative force. So what's the potential energy of gravity? It's mgy, where y is the altitude of the mass m. Y is the distance from ground level. We're taking ground level to be y equals 0. That's the reference point. The reference point is where u is 0. Where is u 0? Well, when y is 0. So that would be ground level, has zero potential energy. As you move up, the potential energy increases. If you move down, the potential energy decreases. And this is the formula that relates the displacement from ground level to the potential energy of this mass at the surface of the Earth. Now, when we go to outer space, the definition of potential energy will be more complicated. So this is really just relevant to gravity near the surface of the Earth. How near is near? Well, where distances or elevations are much smaller than the radius of the Earth. Now, section 5 is on conservation of energy. We combine kinetic energy and potential energy. We call that total mechanical energy. And E is a constant of motion if all the forces are conservative. That's because the change in kinetic energy will be the net work. Change in potential energy will be the negative of the net work. And so if K increases, U decreases by the same amount. Or if K decreases, U increases by the same amount. So E, the total energy, doesn't change at all. And that's an example of conservation of energy. We call it a conservation law. Something is conserved means that it's constant. The energy may change from kinetic energy to potential energy, or vice versa. So the forces are changing, the energies are changing, but the total amount, K plus U, is not changing. And that's a conservation law. Not all forces are conservative. In particular, friction is not conservative. So when there's friction or drag, the mechanical energy changes. It's really the first law of thermodynamics. The energy changes because there's heating when there's friction. When there are frictional forces, there's transfer of energy by heat. And so the change in energy is not zero. It's equal to the amount of heat that's generated. When there's friction or drag, then the final energy will be the initial energy plus the work done by the non-conservative forces. And the work done by the non-conservative forces, like friction, will be negative. So the final energy will be less than the initial energy by the amount of work done by the frictional forces. Then there's one more section, which is just called power. Power is work per unit time. You know, some system is changing, work is occurring. How fast is it occurring? What's the work done in a certain amount of time? So power is just defined as work over time. Or, since work is related to energy, the change of energy, power is the energy supplied divided by the time. Now, units. The unit of energy is called the joule, named after James Joule, famous English brewer. He had a brewery. He made beer. He had a company to make beer. He wanted to find more effective ways to make beer. So he started doing experiments, and he discovered that heat and energy, both of which are used in making beer. They have certain properties, and in particular, there's a conservation of energy. And so the unit of energy, which is not limited to mechanics, but to all kinds of scientific or scientific processes, like making beer is a biological process. It's a kind of biochemical process. Well, energy is conserved unless there's heating. And it was James Joule, the beer owner, who figured all that out. So in his honor, the unit of energy is called the joule. We can relate it to other units. Remember, work has the same unit as energy. Change in kinetic energy is work. So work and change of energy have to have the same unit. So work has to have the same unit, the joule. Because work is kind of like a kind of energy. It's an energy transfer. Well, work is force times distance. Force is newtons. Distance is meters. So the unit joule, we give it a special name, but it could be written as Newton times meter. That's work. Work divided by time is power. The unit of power is the watt, named for James Watt, who invented, or at least developed, steam engines, also at about the same time in the 19th century. Work divided by time, so joules divided by seconds. So 1 watt is 1 joule divided by 1 second. And you'll need to use those units in the Lon-Kappa problems. All right, so if you've already read chapter 5, you should know all of these things. And you should have all of these equations written down in your notebook. Now let's see. Oh, there's one important thing to learn in this chapter, and that is how to use the conservation law to do calculations in mechanics. We define the total energy of a system. Let's just think of a system with one mass, is 1/2 mv squared, that's the kinetic energy, plus U, that's the potential energy, and U depends on X. Kinetic energy doesn't depend on X, but potential energy does depend on X, but not on V. E depends on both speed and position. But E is a constant of the motion. So as a particle moves around in space, its potential energy will be changing because its X value is changing. But E will not be changing. That means V has to be changing. So when X changes, V must also change. It either speeds up or it slows down, so that the combination, the mechanical energy, is constant. And that's the conservation of energy. And that gives you a way to solve certain kinds of mechanics problems, because you can say, well, let's calculate the energy at some arbitrary time. So at some arbitrary time, the energy is 1/2 mv squared plus U of X. Now, let's suppose I know the initial speed and the initial position. Then let's calculate the initial speed, the initial energy. It'll be 1/2 mv0 squared plus U of X0. Now, these two numbers are equal. So I could just say, this is some constant, something we know. If you give me the initial system, the initial velocity and position and so on, then I can calculate this quantity, call it C. And if I write 1/2 mv squared plus U of X at any later time during the motion of the particle, That'll also be c. So you see, this gives me a relation between velocity and position. Back in chapter 4, we had relations between velocity and time. Velocity is acceleration times time. And between position and velocity. Position is the velocity times the time. But it depended on the time. Now I have a relation which doesn't involve the time, but it relates the speed and the position. So that's a relationship that I can use to answer questions about the motion of the system. So let's see, I'm going a little slow here. I'm going to speed up because you probably haven't looked at these problems yet. But these are some problems from problem set 4. Throw a rock from a cliff. Well, we know it's going to follow a parabolic trajectory. It'll come off and go down and hit the ground. Analyze this motion using energy. That's problem 76. And what that problem shows is that you can either specify the potential energy, the reference point, where potential energy is 0, to be 0.2 or 0.1. It doesn't matter if you use 0.1 or 0.2, the motion will be described in the same way. It's just a different reference point. So that comes out of, you do part A, taking potential energy to be at 1. You do part B, taking the reference point to be at the 0.2, and then you compare 1 and 2, and you find they're the same. They give you the same result. Here is a little more physical problem. A frictionless roller coaster with a loop-the-loop. So the roller coaster car, let's just say it's a roller coaster with one car. The roller coaster car starts at some height, goes down the track, gets to the bottom of the track, then it enters a loop-the-loop, and it goes around the loop-the-loop. So you're given this height, 25 meters. Now you're asked, how fast is it moving at point A? And you can solve that by conservation of energy. You can say, at this point, the energy is mgh. It's just the potential, gravitational potential energy. At this point, the gravitational potential energy is 0. But now there's kinetic energy, 1/2 mv squared. Now you know energy is conserved, so 1/2 mv squared plus mgy is constant. So in other words, mgh, that's at this point, is the same as 1/2 mva squared. That's at this point. So you can calculate the speed at the bottom. And you see how easy it is. It's just a very easy one-step problem to calculate the speed here if you know the height here. It doesn't depend on the shape of the track. If I want to know the time to go from this point to this point, I would have to know the shape of the track. But I'm not asked about the time. I'm only asked about how fast is it moving at this point. Well, all I need for that is to use conservation of energy. Part B is to say, what's the radius of the track so that it won't fall off the track at point B? That involves calculating the speed at point B. But you can, again, use conservation of energy. So to get the speed at the top, you just use conservation of energy. At point A, the energy is 1/2 mva squared. It's all kinetic energy. At point B, the energy is 1/2 mvb squared plus mg times 2r, or r is the radius, or 2r is the diameter. or the height. Whoops, what happened? I hope I'm still here. Am I still recording? Yes, I'm still recording. Okay. So you see, I can use conservation of energy to determine from the initial height, the speed at the bottom, the speed at the top of the loop. I have a criterion for the car to remain in contact with the track, and I can see whether the car remains in contact with the track. In other words, the ride is safe. You know, if the car didn't remain in contact with the track, it'd fall off and just crash into the ground. Not safe. So here's a problem that you can do. It does involve circular motion, so I have to use the centripetal acceleration to analyze it. But anyway, to determine the speeds, I just use conservation of energy. Here's another example, a pendulum. A pendulum is a mass attached to a point on the ceiling. It swings back and forth. There are two forces. There's a force of gravity, that's conservative. There's the tension force of the string, but that length is constant. Since work is force times distance, there's no change in the distance. The distance from the ball to the contact at the ceiling is constant. It's the length of the string. So if we assume the string is not flexible, that is to say it's got a constant length, then energy is conserved here. So as the ball swings back and forth, it'll be on a circular motion. As it moves down, the kinetic energy increases and the potential energy decreases. But the kinetic energy plus the potential energy remains constant. So K plus U is K initial plus U initial. If I started at some angle with no speed, I just hold it with my hand out at some angle, and then I let go of it, then it goes back and forth. But while just at the instant when I let go of it, it has no speed. So the kinetic energy is zero. The potential energy is mgyi. You can relate that to the angle theta. That'll be equal to 1/2 mv squared plus mgy at any point along the motion. It's a constant of the motion. You have to relate height, which is y, to angle to analyze it in terms of the angle. But for example, you can figure out the speed at the bottom of the arc. Suppose I pull the ball over by some angle, say 45 degrees, and then let go. Well, then it'll oscillate back and forth around the minimum, around the bottom. How fast is it moving when it's at the bottom of the track? That'll be where it has the largest speed. It's again a question of conservation of energy. Potential energy decreases as kinetic energy increases, but the pair, the sum, is constant. So the initial energy is mg times the initial height. The energy at the bottom is 1/2 the speed at the bottom squared plus mg times 0. We call that the reference point, ground level. So here's an equation for the speed at the bottom. So see how easy it is. It doesn't really involve a lot of analysis. It's just a matter of writing down one equation, equation of conservation of energy. Or here's one more problem, a spring-loaded gun. You have a little gun with a spring in it, and it shoots pellets with some speed. And suppose it's at some height above the ground, how far will it go? Well, again, you can use conservation of energy. First, you pull back the spring. You compress the spring. Then there's a energy 1/2 K delta squared. That's spring compression. When the pellet leaves the spring will no longer be compressed. There's no spring energy involved. You'll just have the kinetic energy, 1/2 mv1 squared. That'll be the velocity or the speed when it leaves the gun. Then it falls down to the ground. Now I could analyze that using chapter 4, it's a projectile, or using chapter 3, or I can more easily just say conservation of energy says 1/2 mv1 squared plus the gravitational potential energy here, mgh, will be 1/2 mv2 squared when it hits the ground. So if all I'm interested in is how fast is it moving when it hits the ground, this equation gives it to me immediately. Now, if I want to know a little more, if I want to know something about the time, then I can't just use conservation of energy. I have to use force and acceleration. But, this is just constant acceleration under the force of gravity. So the acceleration is minus g, downward g. And so I can figure out, it travels a distance h. 1/2 gt squared is equal to h. So that means I can calculate v from the time to fall. And so you see, this is a problem which looks like it's going to be pretty hard because there's a force here, there's a different force here. You're going to have to calculate this changing acceleration here. You have to calculate the projectile problem here. Well, actually, it's not as hard as it looks, because for a lot of it, you can just use conservation of energy. Well, you'll be doing those problems in the next week or so. So I won't say anything more about those tonight. Doesn't seem to be anything there. What did I miss? I guess that's the end. Let's see. There was a question on the chat. The recording is on. Yes, the recording is on. Yeah, I had a little glitch there, but the recording is on. Anybody want to ask a question about energy or the exam or the homework assignments? I mean, you've got to, well, today you have to finish the corrections exam. And everyone should do all the problems on the corrections exam. You should find the corrections exam is pretty easy because you've already done the problems on the exam. And the grades on the exam were fairly high. The average was a little more than 9 out of 12. So you already know how to do the problems. You did them on the exam. Maybe you missed 1 or 2 of them. Well, you have to think about those a little more deeply, but they're not that hard, those problems. And so it shouldn't take you long to do the corrections exam. And that will determine your final bonus points. And then sometime, I guess Saturday, you'll find out your grade on the exam and plus the corrections exam. It sort of looks like there's nothing to do next week. Well, actually, there's a lot to do next week because you have to read 2 chapters. And you actually have to do 2 reading quizzes. I mean, there's reading quiz 4, actually has 2 parts. 4A and 4B. 4A goes along with chapter 5, 4B goes along with chapter 6. And then the next Monday, which I guess would be 6, 7, 8, 9. So here, you'll have the problem sets from chapters 5 and 6. So actually, you have quite a bit to do before the next Zoom meeting. You have to do the readings of both chapters 5 and 6 and the problems of both 5 and 6. So it's kind of a double assignment. You have a little over 2 weeks. You have approximately 2 weeks to do it. But don't procrastinate. Do it now. Get chapter 5 done by early next week, and then get chapter 6 done before the end of the next week. All right, let's see. There's some questions on the chat. We're sort of running out of time here. Can I ask a question about problem set 4, which was due before the exam? I mean, problem set 3. Yes, we can take a question about that. When will the grades be visible? I think Saturday. I was a little confused by the question bank track in problem set 3 that was due on Monday. Oh, that's the one you want to ask about the bank track problem. All right, let's think about the bank track problem. Let's see. You've driven in a car where the exit from a highway is banked. It's on a circle, so it's so you exit from the highway. Let's say you're going this way. You exit from the highway. Oops. And there's a curve that you go around, but this curve is not horizontal, it's banked. So if I look at it from the side, I guess it'd be banked this way, and your car is this way. So here's your car as it's going around the circle. And the circle has some angle. I mean, the street, the road has some angle, theta. So, in all these problems with forces, you have to draw a force diagram. So let's draw a force diagram. Let's put the forces in black. Here are the forces on the car. Well, there's a normal force. Perpendicular to the road, which is banked. So if this angle is theta, then I guess this angle is also theta. If the angle theta were 0, then it would be not banked, and so the normal force would just be straight up. So this angle must be theta. All right, it's got a gravitational force. The magnitude of the gravitational force is mg. We could call this the contact force in the normal direction. Normal is the word that's jargon. I mean, normal is the word that we use for perpendicular to a surface. So again, if I put it in a different color, I guess this would be the surface. And now there's friction. Now, which way is the friction? The frictional force will be frictional force will be that way. So we could call that the force of friction acting on the car. And it's static friction. This is static friction because it's not moving in that direction. It's not skidding. In other words, it's not skidding down, it's not sliding. All right, so if I look at the normal force and then minus mg cosine theta, well, there's no acceleration in the normal direction. So the mass times the acceleration would be the force. That has to be 0. And then if I look at the tangential force, I have, let's see, what do I have? I have tangent to the road. I have the force of friction. That's tangent to the road. And then I have the component of this force, tangent to the circle, which I guess would be plus mg sine theta. And that has to be no, that's not going to be the right way to do this. Well, that's going to be okay for the, I don't really want this. There's an acceleration because the car is moving in a circle. It's v squared over r. So the other equation I need is m v squared divided by r. That's this radius, r. That's the mass times the acceleration. That has to be centripetal force, which is the force of friction. It's in this direction. So if this angle is theta, I guess this angle is 90 minus theta. So it'll be this force of friction sine of theta. And now the way static friction works is that the force of friction has to be less than the coefficient of static friction times n, or times, I should say, times f n. So you see, I have three equations really. I have this equation for the normal force, and there's no normal acceleration. So the acceleration is 0, the force, I have a normal component of gravity. Then I have this equation for the, I guess that would be the x component or the horizontal component, because it's moving in a circle. So it's got to have a centripetal force towards the center of the circle. So that's the centripetal force. I don't think I've analyzed this quite right. I don't think I've completely done this, but here's, these are the essential parts of that problem. You have to draw a force diagram, separate the forces ultimately you have to solve this equation. F vector equals m times the acceleration vector. And the acceleration vector for centripetal acceleration vector is negative v squared over r in the r hat direction. So you're analyzing this equation of motion for the centripetal acceleration, and you have to analyze the forces on the car when it's on the surface. And since it's on a sloping surface with an angle theta, you'll have normal component, frictional force, and the gravitational force is vertical. So you have to separate the vectors. You'll eventually have to have two components giving you two equations. So that's kind of a difficult problem. That's kind of a that's a problem where you have to put together many things. All right, any other questions? We've gone over 5 o'clock. We've gone past 5 o'clock, so I think we should end the meeting now. Let me start by ending the recording.